Okay, so in this lecture, I'm going to introduce the very first ideas that lead to the null hypothesis significance test. And I will bring you to the point where you can do a one sample t-test by the end of this lecture. So let me start sharing my screen. Right. So, so here are the slides. I'll be providing the slides to you on Moodle as well as the source code behind it so you can rerun all the code yourself. So the, the interesting issue that is the beginning of the entire story of hypothesis testing in the Frequentist framework is that what we typically do when we do an experiment is that we collect a sample of data. For example, the Stroop data that we collected in class, right? So there we have a single sample, one sample, right, of data. And once you've collected this sample, we know how to compute the sample mean and the sample standard deviation, which I'm always going to write, or sometimes I'm going to write as mu hat and sigma hat. So whenever we are computing estimates of particular parameters, those are marked with a cap here like this, okay? So these, as I explained earlier, these are maximum likelihood estimates. And so that's always the first step. The estimation step is the first step. We get estimates of the unknown mean, unknown mu parameter and unknown sigma parameter, for example. And we use those estimates to do some statistical inference, as I will just show you. So the situation I want you to imagine now is that we don't take a single sample. Right now, in the Stroop experiment, we did only one experiment with 31 or 30 subjects. We are not going to take a single sample, but we are going to repeatedly do the same experiment over and over again. So you can imagine collecting data repeatedly from new subjects or from the same subjects. Right now, that doesn't really matter that much. But what I want you to imagine is repeated collection of the same data, of the repeated collection of the data from the same experiment design. Now, suppose that we do these repeated samples, right? We collect these repeated samples and we compute the sample mean each time, right? So let's simulate that situation. We can run experiments on the computer without actually collecting data physically the way we did for the Stroop experiment. So we're going to use the rnorm function to generate 100 data points from a normal distribution with mean 500, standard deviation 50. These are just arbitrary numbers I chose just as an example. And this is one sample. Okay, this counts as one sample of sample size 100. And once I've collected this sample, I can compute the mean, I can compute the standard deviation, etc. Those are the MLEs, the maximum likelihood estimates that we can compute. Now, if I did the same thing that I've done here one more time, that's here, what you'll see is that my sample mean will vary a little bit, right? That's because of random variability. Whenever I'm collecting data repeatedly, each time I'll get slightly different numbers. And as a consequence, the sample mean is going to keep varying, right? So let's do this procedure that I did twice. I collected two samples. Um, let's do this multiple times. So let's do this 1,000 times. Okay, we're going to do 1,000 simulations. That means we're going to collect data 1,000 times. And we're going to collect data from a normal distribution with a particular mean and a particular standard deviation. So I just chose some values here. It doesn't really matter what you choose for the purposes of this demonstration, right? And what I'm going to do is, so this is where all the for loops and all the other R coding that you learned is now going to come in handy, okay? So we're going to do 1,000 simulations, and we're going to collect 100 data points in each uh, sample that we collect. And each time that we collect 100 data points, we're going to compute the mean, and we're going to store that mean in a vector, which I'm calling the sampling distribution of the means. So basically, I've created a vector here with 1000 cells, right? An empty vector with 1000 cells that is going to, once the for loop runs, it's going to end up containing the the means from the repeated samples. Okay, so I've set up my sampling distribution of the means, right? I've also created a new vector for storing the sample standard deviations, but this is of less importance right now. I just did it because you could actually store that information as well in a separate vector. Okay, so let's just focus on the sampling distribution of the means. So when I run this for loop now, this for loop will run for 1000 iterations. Okay, and each time, each of those 1000 times, it will collect 100 data points from this distribution, compute the mean of that distribution, and save that mean in the ith cell of the vector sampling distribution of means. So once this for loop runs, I will have 1000 means in this vector here. Okay. So the interesting thing is, if I plot the distribution of these means under this kind of repeated sampling, if I plot the distribution of the means, the distribution of the means, which I'm characterizing on the x-axis as mu hat, okay? Because each of these numbers that constitute this distribution, they are actually estimates, sample means from the samples that I've taken, from the 1000 samples I've taken. So these are all sample means that I'm drawing the distribution of. And so what I notice is that the sample mean, the distribution of the sample mean has a normal distribution. So what's interesting about this is that earlier, in this simulation here, I had sampled from the normal distribution. But let me now sample from a distribution that is not normally distributed. So I'm going to take samples from an exponential distribution. So I'll show you what it looks like. An exponential distribution looks very different um, from a normal distribution, right? So if I take 100 samples from a normal distribution, right? Let's just take the standard normal as an example. So these are my samples. If I draw the histogram, this looks Gaussian. But if I had taken a sample from an exponential distribution, let's take 100 samples from the exponential distribution, and I draw the histogram of this distribution, that is not a normally distributed. Uh, that's not normally distributed data. So what I'm doing now is I'm taking samples from such a distribution repeatedly. Each time that I take these samples, these 100 samples, I'm going to compute the sample means and again plot the sampling distribution of the means. What's surprising is that the sampling distribution of the means will still be normal. It'll still be normally distributed, right? So here I'm doing 1000 simulations, sampling 100 data points each time from the exponential distribution, and computing the sample mean and saving it in the ith cell of the vector sampling distribution of the means. I'm ignoring the standard deviation right now. It's not really the important thing. So So what you notice again is that despite the fact that the underlying distribution that I was sampling from was an exponential, I nevertheless get a sampling distribution of the means under repeated sampling that is normal. So really, it turns out that it doesn't matter which distribution you're sampling from. Can be an exponential, it can be a gamma, it can be a log normal, it can be anything, any distribution, basically any distribution. And what will happen is that the distribution of the means under repeated sampling will always be normal. So this is a key result, in statistics. It's called the central limit theorem. And what it says is that for large enough sample sizes, the sampling distribution of the means will be approximately normal, regardless of the underlying distribution. And one condition here that I kind of neglected to mention is that the underlying distribution needs to have a mean and a variance defined for it. So there happens to be one distribution, that doesn't have a mean and variance defined for it. That's called the Cauchy distribution. So if I take, samples from the Cauchy distribution, this distribution will have, um, basically it'll have wildly varying numbers. You see that? It's very different than the standard normal. Most of the values are near zero, but occasionally you'll get really large numbers here. You see that there, right? So you'll get very wild numbers in this distribution, and the mathematical properties of the Cauchy distribution are that it has no mean and variance defined for it. So the central limit theorem doesn't apply for that distribution. Okay, so apart from the Cauchy, which we don't care about in this course, right? um, as long as we have a distribution that we're sampling from that has a mean and variance defined for it, as long as the sample size is large enough, the sampling distribution of the means will be approximately normal. So let me show you an example of when the sample size is not large enough and we are, let's say, sampling from an exponential distribution. What's going to happen to the sampling distribution? Is it going to be normal or not? Let's take a look. Okay. So let me first copy this code off, right? Just gonna copy all this here and run it here in, just on this command. No, let me just write it in this example. Yeah. Right, so, oh, sorry, that's not gonna work. Right, so now I'm going to sample from an exponential distribution, right? And let's look at, we're going to sample from the exponential distribution. Let's remove the standard deviation section. We don't really need it. Let's focus on this, okay? So now, right now I'm taking samples from 100 data point, samples. I'm sorry, what's wrong now? Right, so right now I'm taking samples of size 100. You see that here, right? Size 100, right? So let's do that. Once I do this and I plot the histogram of the sampling distribution of the means, you'll see that it's roughly normally distributed, right? But suppose I change the sample size to, I don't know, 5. That's a small sample size, right? Let me rerun this. And now what you will see is that there's the sampling distribution of the means is no longer normal because there's this right skew here, you see this skew here. This skew is basically illustrating the condition that I just explained to you in the central limit theorem for large enough sample sizes. So if you have a large sample size, you are guaranteed to get a normal distribution for the sampling distribution of the means under repeated sampling, regardless of what the underlying distribution is that you're sampling from. This is actually, this amazing result is actually the basis, for null hypothesis significance testing. So let's get to that point now. So once we've, computed the sampling distribution of the means, let me do that again now with this exponential, or let me just do it with the normal, just because what we had was the normal distribution. It's easier to keep track of what's going on here because you're familiar with the normal distribution, right? You've already studied this. So let's work with the normal distribution. We're going to take a sample of size 100. We're going to do 1,000 simulations, so 1,000 repeated samples, and we are going to take samples from the normal distribution, compute the sample mean. Okay, what did I do wrong now? Uh, Let me start over. Oh, sorry, this I'm not paying any attention to what I'm doing. It's hard to talk and write at the same time. Right. So, so what we see is a sampling distribution of the means that is roughly normal. So one question you can ask yourself now is, what's the mean of this sampling distribution? Well, it should be close to 500. We can see that already, right? The largest density region is this around 500. So if I computed the mean of the sampling distribution, it would be near 500, right? But I can also compute the standard deviation of the means. That means what I'm now computing is the variability in the means under repeated sampling. So that's the standard deviation of the sampling distribution of the means, right? And that is the number 10 here, right? So that's the sampling distribution, the standard deviation of the sampling distribution of the means. Now, it turns out that this standard deviation of the sampling distribution of the means is called the standard error. And the standard error is basically the square root of the standard deviation. Sorry, it's the not the square root. It's this quantity. It's the standard deviation of the underlying distribution that generated the data divided by the square root of the sample size, which in this case is 100, right? So n is 100 here. So that's why I just wrote square root of n here, right? So this quantity, 100 divided by the square root of n, is going to be the true quantity that we are estimating when we compute the standard deviation of the sampling distribution of the means, right? So the standard error is equal to the standard deviation of the underlying distribution I'm sampling from divided by the square root of the sample size. Okay, this is an analytical result in statistics. This can be proven, but I'm just showing this to you. I'm demonstrating this to you right now, just through simulation. So let's take a look. Our standard deviation of the sampling distribution of the means is about 10.12, right? Let's find out what the actual true value would be. So in this case, we can talk about the true value of the standard error because we know the true value of the standard deviation of the underlying distribution. Because we are in a situation where we know the gold standard values that produce the data. So we can actually use the true underlying standard deviation and divide that by the square root of n, and that should be very, very close to this empirical value that we get through actual simulation, right? And so what we get is the number 10, right? So this estimate of the standard deviation, which is called the standard error. The standard error is just the standard deviation of the sampling distribution of the means, okay? So the standard error has an analytical value that we are estimating from the repeated sampling that we just did. So it's actually even more amazing. What is really interesting about the frequentist setup is that from a single sample, I'm no longer talking about repeated sampling. From a single sample, we can get an estimate of the standard error. What that means is that once I've collected a single sample, like the Stroop data, I can actually describe the distribution of the means that I would get if I were to, counterfactually, if I were to repeatedly run that experiment. So by running a single experiment, I'm able to describe the properties of the sample mean under hypothetical repeated sampling. And by describing the distribution of the sample mean, I mean that I can compute the mean of the distribution of the sample means. That's just my sample mean that I have from that one sample. That one sample gives me a sample mean, and that is a reasonable estimate of the mean of the sampling distribution of the means, this quantity here, right? This distribution here. And the standard deviation of the sampling distribution of the means, I can compute from a single sample because I have an estimate of the standard deviation that I have from the data, and I know the sample size. So therefore, I can actually compute an estimate of this underlying true value, right? So in practice, what will happen is that you might actually collect, let's say, 100 data points, right? So let's say I collect 100 data points, right? That's my 100 data points. And so now if I compute the mean of those data, I get an estimate of the underlying mean that produced the data, the underlying mean of the distribution that produced the data, right? Of course, this need not be an accurate estimate, but it's the maximum likelihood estimate. It's the best I can do, right? Also, I can compute the standard deviation of this distribution, right? And the standard deviation of the distribution is 105. That's an estimate of the standard deviation. I don't know the true standard deviation. I don't know the true mean. I'm just estimating it from the data. But this estimate is actually enough for me to write down the standard error estimate, which is square root of 100. So that's how I end up with an estimate of the standard error and of the underlying mean. These are all estimates of the standard error of the underlying distribution of sample means, right? So graphically, what's going on is that I took a single sample. I took a single sample. So a vector of size n, right? So x1 to xn, right? That's my vector of size n. I compute the mean, which I'm going to call x bar. I compute the standard deviation. I know the sample size, and this information allows me to compute the allows me to describe the distribution of the sample means under hypothetical repeated sampling. So from a single sample, I can suddenly start talking about the distribution of the sample means under hypothetical repeated sampling. So really, this estimate, this distribution gives me my best estimate currently, given the data, of what the variability in the sample means would be, right? Variability in the sample means would be under repeated sampling. So this is an amazing thing because with a single sample, you can describe how variable the sample mean would be if you were to rerun the experiment over and over again. But you're never going to rerun the experiment over and over again, right? Normally, when we run a study, that's it. We are done with that study. But from that one study, we can draw an inference about the variability in the sample mean, and more specifically, we can actually define our best guess of the distribution of the sample means through the central limit theorem. So this result here is very important because it tells us what would happen if we were to run the experiment over and over again. And we get the information about that, the distribution of the sample means from a single sample. Of course, you have to remember that if this estimate is incorrect and this estimate is incorrect, then obviously we are not close to the true distribution. But that doesn't matter because this is the best we can do. Once we have the data, this is the best guess we have of the underlying distribution of the sample means. All right. So this is actually quite a deep idea. So you have to like really sit down and meditate over it a little because it will have really important implications in the coming part of this lecture. Right, so this was the scenario that I was talking about just now. From a single sample, we can compute the sample mean, we can compute the sample standard error, right? So the estimated sample standard error from the estimated standard deviation and the sample size, right? Which we will, of course, always know, right? Okay. Also, one other important thing to notice here is the This standard error is telling you how variable the sample mean would be under repeated sampling. If you increase the sample size, what will happen to the standard error? It's going to get smaller and smaller because the n, the square root of the n is in the denominator, right? So as n increases, this quantity, the standard error is going to get smaller and smaller. So what that means is graphically, let's take a look, okay? Graphically, what this means is if I do an experiment with sample size 5, let's say, then I'll get a particular variability. The standard error will be whatever the standard deviation is divided by the square root of 5. So now if I increase the sample size to 50, what will happen now? Now the standard deviation, the standard error will become much smaller because this quantity is now 10 times larger, right? Instead of 5, I've gone to 50 now, right? So what will happen is that the standard error will become tighter and tighter, smaller and smaller. So the practical consequence of that is that as you increase n, right, as n increases, the standard error will become smaller. And what does that mean? What is the implication of that? The implication of that is that if you have a large sample size, the variability in your sample mean will go down under hypothetical repeated samplings. That means that when you have a very small standard error, that means that if you were to run the experiment over and over again, you would keep getting values near the sample mean that you actually have. If you have a very large standard error, what that means is that under repeated sampling, you would get a lot of variation in the sample mean. Sometimes it would be very large, sometimes it would be very large in the opposite direction, sometimes it would be in the middle somewhere. So there's a lot of variation possible. That's the practical implication of the standard error here, which will become very important for us in a moment. Okay. All right. So, so the upshot of all this discussion is that from a single sample of size n, where where we have some mean and some standard deviation, some mu and some sigma that's producing the data, we can estimate we can get an estimate of the mu, that is the sample mean. We can get an estimate of the sigma, that is the sigma hat or S. I'll sometimes call it S, sometimes sigma hat, right? And so those estimates allow us to compute the standard error, an estimate of the standard error. That's what I'm doing here. And they allow us to describe the sampling distribution of the means as I explained earlier, right? So we can actually describe the sampling distribution of the means from a single sample. I'm going on saying this over and over again because it's really important to understand that we are working with a single sample, and from that single sample, we are talking about the hypothetical distribution of sample means under hypothetical repeated sampling, okay? All right. So one very important, quantitative summary that you will see in papers when you're reading articles is the 95% confidence interval. So when we're talking about the Stroop data, right? So in the Stroop data, let's say the difference between the congruent and incongruent conditions, the difference between the congruent and incongruent conditions could be 100 milliseconds, for example, right? So in a paper, if I were writing a paper on the Stroop test, I would actually write alongside the estimate. This is the estimated difference, between the congruent and incongruent, sorry, the incongruent and congruent conditions, because it's positive. That means the incongruent conditions are slower than the congruent conditions, right? So I would write two numbers, which I'm just writing as lower and upper here. I would write two numbers which represent a 95% confidence interval, okay, which I'll call a CI from now, okay? So the 95% confidence interval is something that you will often see reported alongside an estimate of a difference of sample means, right? So the difference of sample means here is the difference between the mean of the incongruent condition, the mean of the congruent condition in the Stroop test, right? So the way we report this in the paper is by saying that the 95% confidence interval is, and usually in square brackets, you put the lower and upper values, right? So where that comes from is that, remember, I just said that the sampling distribution of the means is going to be normal, is going to be normal uh, with some mean mu and some standard error sigma over square root of n, right? So this is the true distribution. This is the true distribution that we are estimating, sorry, true distribution of the sampling distribution of the means. Of course, we do not know the true distribution ever, right? We are always estimating the mu and sigma parameters, right? And that's why what we're actually working with is estimates of mu and estimates of sigma. So we are working with an estimate of these parameters. But uh, one one thing that is true, even though we have estimates here, one thing that is true is that we have a normal distribution for the sampling distribution of the means, right? So if the distribution of the means, right, mu hat, I could write this as mu hat or a capital X bar. It's the same thing, okay? So the distribution of the means um, is normal. And what that means is that 95% of the area under the curve is covered by 1.96 times. So this is the center point here, right? Oh, sorry, you can't see anything, can you? I'm so sorry. Um, I guess I should start over because I talked about all this and I didn't actually show you what I was doing. So what I'm saying is, let me start over. Sorry about that. Right, so what I'm saying um, is that whenever we do a single experiment, we are actually working to figure out what the sampling distribution of the means is. Okay, that's what we are trying to figure out. Now, these parameters, the parameter mu and sigma, we do not know. We can never know them. Otherwise, we wouldn't need to do any data collection, right? If we knew what those parameters were. The whole point of data collection is to estimate some parameters so that we can learn about the world that we are studying, learn about the problem that we are studying. So instead of the true values of mu and sigma, what we are actually working with is estimates of mu and sigma, right, from the data. And so the important thing though is that because the distribution is normal, certain properties of the sampling distribution have to be true. And what are those properties? Well, one property is that the that 95% of the area under the curve, 95% of the area under the curve, this area under the curve, right, is covered by going from the center point of this distribution. If you go 1.96 times the standard error, right? Remember that the standard deviation of the sampling distribution is the standard error here. So 1.96 times this standard deviation. And if you go minus 1.96 times this standard deviation, right? You get to the lower and upper quantiles here, which represent the 95% confidence interval. Okay, so they basically cover 95% of the area under the curve. Now, because 1.96 is not very different from 2, right? I tend to just use 2 times plus 2 times sigma over square root of n and minus 2 times sigma over square root of n, right? So now, as I just mentioned, we don't actually know what sigma and mu are. So when we report our sample mean, which I'm calling mu hat here, right? What we would be reporting is plus minus 2 times the standard error, the estimated standard error. So these are all, these values and these values, they're all based on estimates from the data. They're not the true values here. Here, I'm writing the true values. This is the true value. This is the true value of sigma, true value of sigma. We don't know those true values, right? So we are working with estimate. So what we report in papers would be the sample mean or the difference in sample means, like in the Stroop task, and a 95% confidence interval around that sample mean. Okay, so that's what I wanted to get across here. That this is a very common summary statistic that you will see in papers reported alongside, the sample mean or the difference in sample means. So let's compute a 95% confidence interval in our data, right? So let's take a sample of size 100. So I'm just taking a fresh sample, okay? Just to simulate a real life situation. I collect my sample. I compute the sample mean, which I'm calling mu hat. I compute the sample standard deviation, which I'm calling mu hat sigma, right? Oh, this is funny. Sorry. It's very foolish of me to actually have mu hat here and hat sigma here. I should have written sigma hat here. I'll just fix that, okay? I'll just fix this after the lecture. Sorry about that. And so what I'm doing here is I'm computing the lower bound of the 95% confidence interval. How do I do that? I take the estimated sample mean and subtract from it minus 2 times the standard error, the estimated standard error, of course. Whenever I say standard error, I always mean estimated standard error because I never know the true standard error, right? Because I don't know the true standard deviation, right? But I tend to get sloppy and just say standard error. But what I really mean is estimated standard error. We will never, ever, ever know the true standard error because we don't know the true standard deviation. So that's why it's kind of redundant to say estimated standard error each time. It's always estimated, right? So that's why I will get sloppy about that, okay? So the lower bound of the 95% confidence interval is 492, and the upper bound is the sample mean plus 2 times the standard error, right? So that's exact. I'm just computing this quantity here, mu plus minus 2 times the standard error, right? Of course, as I said, technically it's 1.96 times, okay? But I don't really care. So I would just say 2, right? It's close enough, okay? So now, the important thing I want to get across is the meaning of the 95% confidence interval. Unfortunately, the meaning is very convoluted, and so I'm going to explain this now, okay? So the 95% in the 95% confidence interval, what it means is that if you were to repeatedly take samples from the original distribution that was producing the data, and each time if you were to compute a 95% confidence interval, so you see that I did that once here, I computed a 95% confidence interval. Suppose we do this repeatedly. Each time we compute a 95% confidence interval, okay? And let's say I store all those repeatedly computed confidence intervals in a matrix, right, in a data frame or something. 95% of those confidence intervals 95% of those confidence intervals that were computed under hypothetical repeated sampling would contain the true mean, the true mu of the underlying distribution that produced the data. Right? So let's do this, okay? Simulation to help us understand this. I'm going to create a vector lower and a vector upper that will store my lower and upper bounds of the confidence intervals. For 1,000 simulations, I'm going to take a sample size of size 100 from the same normal distribution. Normal just for illustration, okay? It doesn't really matter right now for us what distribution we are sampling from, as long as it has a mean and a standard deviation, okay? So I take a sample, compute the sample mean, and compute the lower bound by computing the sample mean minus 2 times the standard error. Okay. And do the same thing to compute the upper bound. So mean plus 2 times the standard error. So I've got a vector of 1,000 values here and 1,000 values here. Is it 1,000? Yeah. So 1,000 values of lower and upper bounds, right? And so now I'm going to, I know what the true mu is. Remember the true mu is 500 or whatever it was, right? So what I'm checking here is in this if else command, I'm checking what proportion of times do I have the true mu landing within the confidence interval. So if the true mu is larger than the lower value, and if the true mu is smaller than the upper value, then it lands inside the confidence interval, right? And so whenever that's true, I will record a 1, otherwise I'll record a 0. And so what should happen is that in about 95% of the cases, I should get a 1, and in 5% of the cases, I should get a 0, right? And so let's do this, okay? So I've computed a sequence of ones and zeros. 1 means that in a particular confidence interval, I got the true mu landing inside it, and 0 means that I didn't land inside it. And so if I look at the summary of this table, I'll see that about 95% of these 1,000 simulations, 95% of them contain the true mu, right? So, and I can even compute the proportion. That's what I'm doing here. So about 95% of the confidence intervals happen to contain the true mu, right? That's the meaning of the confidence interval. So what's weird about this? And so here is the result graphically. Okay, so what I've done is I've done earlier I had done 1,000 simulations. Now I'm doing 100 just because it's easier to see 100. If I'd done 1,000, all the vertical lines would get cramped up together, so it's hard to see what's going on, right? So what I've got 100 simulations here, and what you notice is that most of these confidence intervals, these are the confidence intervals, most of them actually contain this true mu. So this time I used a mu of 60 because the underlying distribution mean, the distributions mu and sigma, they could be anything. We don't know what they are, right? So instead of using 500, I'm using 60 here just for illustration, right? That it could be anything. The true mu could be any value. So that's this horizontal line, the true mu. And what you notice is that most of the time, the confidence intervals computed under repeated sampling contain the true mu. But there are a few, there are one, uh, 2, 3 cases in these 100 simulations that do not contain the mu. Those are the thick lines that I've got there, right? So you can see that this thick line does not contain the true mu. So 95% of these confidence intervals contains the true mu. That's the meaning of the 95% in the confidence interval that we report, right? So, so what's strange about this, right? This is a very strange thing to talk about because the 95% confidence interval that we compute from a particular sample is not telling us that the true value of the mu parameter lies within that particular confidence interval with probability 95%. That's not what it's telling us, right? So, and I mean, that's what we would want it to tell us actually. Intuitively, as human beings, what we would want to know is something like this, okay? So if I report to you that in the Stroop task, the incongruent minus congruent conditions have a sample mean of 100, that means on average, the slowdown is about 100 milliseconds. And if I tell you that the 95% confidence interval is between 50 and 150 or something, right? Let's say, I'm just making these numbers up, okay? So suppose I say that my 95% confidence interval is this quantity, this range here, right? So intuitively, what I want to interpret this as is that this interval tells me the uncertainty I have about the true mu, the true difference between the two conditions. But that's not what it's telling me. This confidence interval, the 95% here, right, is just representing what would happen if you were to repeatedly run the experiment, compute a confidence interval each time. 95% of those intervals, which you did not compute, of course, right, would contain the true mean. But what this particular confidence interval is actually telling you is the uncertainty of the sample mean under repeated sampling. Because remember, the confidence interval was drawn using the distribution of the sample means. So if the confidence interval is very broad, right, it says goes from 50 to 150, right? What this is telling you, and the mean is, let's say, 100 in my example, right? What this is telling you is that under repeated sampling, your sample mean is likely to vary a lot from 50 to 150 with probability 95%. However, it doesn't tell you anything about the probability that your true mu, your unknown mu, lies between these values. This, so what I'm trying to say is that people think that this is what the confidence interval tells you, but this is not what the confidence interval can tell you. And the reason for that is that mu is a constant value. It's an unknown constant, right? It's not a random variable. For us to make statements like these, mu would have to be a random variable. So for example, the 95% confidence interval does actually tell us, it does tell us the following. It does tell us the variability of the sample mean, right? The probability that the sample mean would lie between 50 and 150 with probability 0.95, that it tells us for sure, because this is a random variable, but mu is not a random variable, right? So we cannot talk about the probability of mu lying between 50 and 150, but we can talk about the probability that the sample mean lies between 50 and 150 because this is a random variable. Right? Because it's only random variables that have probability density functions or probability mass functions associated with them. Constant numbers don't have probability density functions associated with them, right? So for example, if my height is 165 centimeters, okay? My height is 165. That's just a number. So you can't associate with me some probability density function for my height. Like my height doesn't keep changing from day to day, you know? And so if I was in a magical universe where my height just keeps magically changing, every day. One day I'm 165, one day I'm 175, one day I'm 155, then there's a distribution associated with my height. So then my height is a random variable. But that's not the case, right? In the natural universe, it's just a number. So in the same way, the sample mean is a random variable. So X bar is a random variable, but the underlying mu that we are trying to estimate with the sample mean, that is not a random variable. Therefore, we cannot talk about a probability density function, associated with that. All right, so this is a very important point because many people often misunderstand that they often think that the 95% confidence interval is telling us this quantity here, but that's not correct. That's not correct. What it's telling us is this quantity here. Okay. So the practical consequence of all this, right, the reason I'm harping on and on about this is that when you see a reported confidence interval like this one, let's go back here to my iPad, right? So let's say I report a 95% confidence interval like this one, my fictional example from before on the Stroop task, right? The way to interpret this confidence interval is to treat it as a measure of your uncertainty about the sample mean under hypothetical repeated sampling. This is the sample mean. So what the confidence interval tells you is how variable your results are likely to be if you were to repeatedly run the experiment, right? That's very important information because, so imagine that when you run your Stroop task and you get a confidence interval of 50 to 150, right? That means that there would be a lot of variation in your sample mean if you were to run the study over and over again. But if you had run a much larger study and your standard error was much smaller, and let's say, I'm just taking a ridiculous example now, okay? But let's say your 95% confidence interval goes from 99 to 101, right? So now you have a very tight confidence interval around the sample mean. And what that's telling you is that unlike the first case, so this is the first case, in the second case, we actually have a much, much tighter estimate of the sample mean. And that means there'll be very little variability if you were to repeatedly run this experiment. And that's good. That's good news because that means that we have a very good estimate of the underlying mean, right? That we are trying to estimate from the sample mean. So the upshot of all this is that the confidence interval is a very important quantity to help you understand how precise your estimate of the true mean is that you got from the sample mean. That's the key point here. Okay? All right. So to summarize, the story so far, when we collect some data, we compute the maximum likelihood estimates of the underlying mu, right? That is the mu hat, or what I call X bar. We compute the variance, right? The estimate of the sigma squared, which I'm calling sigma squared hat, right? And I'll sometimes write that as S squared as well, just to emphasize that it's just an estimate from the data, right? But I could have written mu hat and sigma hat. So I use those two things interchangeably because you'll see both versions, in the literature. And so once we compute the X bar and the S squared, right? So the sample mean and the sample variance, we can um, um, we can now describe the sampling distribution of the means under hypothetical repeated sampling. And we do that by computing the sample mean and computing the estimated standard error. That's step 2 over there, right? Once we have these two pieces of information, we can describe the 95% confidence interval around the sample mean, right? And that interval would be X bar plus minus 2 times the standard error. Well, technically 1.9 times the standard error. But as I just said, I will always use plus minus 2. And so this is actually what we have done so far is estimation. We've just estimated the sample mean. We've estimated the uncertainty of the sample mean under hypothetical repeated sampling, relying on the central limit theorem, because we have a guarantee that the distribution of the means is normal under certain conditions. And we also know what the standard deviation of the sampling distribution would be. That's the estimated standard error. Okay? So this is the estimation step. Now we're going to move on to null hypothesis significance testing. That's the next part of this lecture. Right? So just to repeat, I'm just trying to hammer home this point now, right? What we have learned so far is that we know what a random variable is, and we can distinguish between random variables and constant values, right? Like the mu and the sigma are not random variables. They are actually unknown fixed values out there in nature. We're trying to estimate them from the data, right? And the data that we are observing that's coming from some particular distribution is certainly a random variable, right? So it has probability density function or probability mass function associated with it. And we can, you know, figure out a lot of properties of that distribution from the data that we observe. That's what we are trying to do here. We're trying to learn from data. Right? All right. Um, I'm running out of power, so I've got to connect to the power. Right. So, and also one important thing we learned about distributions was that we learned how to compute the area under the curve, like the probability of x being less than some value, being some value or less than that, or larger than some value or larger than that, or the probability in a particular probability density function of landing between two quantiles, right? Q1 and Q2. All this stuff we have learned how to do, with the different functions that I showed you earlier, the DPQR family, right? We also learned the meaning of the maximum likelihood estimate, the sample mean, and the sample variance. These are maximum likelihood estimates of the true unknown values, right? And we learned about the sampling distribution of the sample means. That's a very important idea that I'm going to now build on in the next part of this lecture. Okay? So in hypothesis testing, the starting point will be that we take a random sample of size n, and let's assume that the data are coming from a particular distribution. For simplicity, I will continue to assume that the data are coming from a normal distribution. I will relax that assumption later on. Okay. So the data are coming from some distribution, let's say a normal, with some unknown parameters, mu and sigma, that describe the underlying distribution that produced the data. Okay. So we will, as always, we'll start by computing the sample mean, compute the sample standard deviation, right? And that will allow us to describe the sampling distribution of the means. That's what I've done here, okay? I hope that this part is very, very clear in your minds, that from a single sample, we are going all the way to this hypothetical distribution of the sampling distribution of the means, okay? That is a very important idea. Now, so let's do this. Now let's actually do an experiment on the computer. So we're doing a simulated experiment here. And it is very important right now to notice that I'm taking independent random samples from some random variable. And I'm assuming some particular distribution, normal distribution for those data. So I'm taking 11 independent data points. That's my sample here from a normal distribution with mean 12 and standard deviation 10. Again, arbitrary numbers, okay? I just chose something, right? So let's compute the sample mean from this particular sample. Of course, when you do this at home, you'll get different numbers, of course, right? So I'll get my sample mean here, 11.25, and I can estimate the standard error, which is 2.69. This is all stuff that we've done before, right? Now, the null hypothesis significance test works like this. You first set up a null hypothesis, which is H sub 0. This is my null hypothesis, which asserts that you believe that the unknown parameter mu that produced the data, this unknown parameter mu, here, of course, I know what the parameter is because I'm simulating some data. But in real life, what happens is that we don't know what the underlying parameter is. And so what we are going to do is we're going to set up a hypothesis that the true value of mu is some particular value. And now we're going to check in our, based on our data, we're going to check whether we can find evidence whether the true mu, whether our null hypothesis is true or not, right? That's what we are trying to figure out. We set up a null hypothesis. We're going to collect a sample of independent data, compute the sample mean, and try to find out if our sample mean is consistent with the hypothesized mean or not. Okay, so I'm going to make precise what it means to be consistent with the hypothesized mean. Okay. Intuitively, what will happen is it should make sense that if my sample mean is very far away from the hypothesized mean, then I would be very skeptical about this null hypothesis in equation 4. But if my sample mean is very close to the hypothesized mean, then maybe it's possible that my null hypothesis is true. Okay, I'm going to make this idea very precise in the next part of this lecture. Right, so I was at the point where I talked about setting up a hypothesized value for mu. And what we want to do is once we've collected some data, we compute the sample mean and we try to find out whether our sample mean is near the hypothesized value or far away in either direction, right? So that's the goal here, to figure out the distance between the hypothesized and the observed sample, hypothesized value for the mu and the observed estimate of mu, which is the sample mean. Okay. So graphically, what this amounts to is that when we set up a null hypothesis that mu is zero, what we are effectively saying is that the sampling distribution of the sample means is centered on zero. So what I've drawn here is the sampling distribution of the means. And what we want to know when we do the hypothesis test is how far away the sample mean is from the hypothesized value, right? So this distance is the thing of interest here, right? Now, how would we compute this distance? You know, the sample mean minus the hypothesized mean, that's the distance that we're interested in, and we want to quantify this distance as far or near. Now, one thing to notice is that the distance will depend on the scale of the data, right? So to give you an example, suppose I'm taking a sample of 100 data points from mean 500 and standard deviation 100, right? And suppose my null hypothesis is that mu is zero, right? Of course, it's not zero, but suppose that that's my null hypothesis. So I take my sample, okay? And then I compute the distance between the sample mean and the hypothesized mean. That distance is 496, right? But that distance is um, actually, that looks very large, right? But now suppose that I were to normalize this distance by dividing it by the standard error. The standard error is going to be the standard deviation divided by the square root of the sample size, which is 100, right? So if I standardize this distance by the standard error, right, the distance is actually much smaller, right? So because this distance is now what we say is that this distance is normalized. It's normalized in the sense that we are now uh, um, correcting for whatever the standard error is, and we are we are looking at the distance in the situation where the standard error is 1. Okay, so that's what normalization does here. Okay, so so what I'm trying to say here is that looking at the raw distance on the raw scale is not going to be super informative. We want to normalize the distance by dividing it by the standard error. And you'll see the stark difference, you know, between the distances between the hypothesized mean and the sample mean in this case. So the distance is quite large here, which is unnormalized distance, right? By comparison, suppose I was collecting data where the true mean and standard deviation were 0 and 1, right? The, the distance now would be very small here, right? So this looks like a very small distance, right? But we could, if we were to standardize this distance, right? We are now in the position that we can actually compare this distance on the same scale when we are comparing the distances between the two distributions here, right? So in this distribution, the mean, sorry, where is it gone? So in this distribution, the mean is 500 and the standard deviation is 100. In this distribution, the mean and standard deviation are completely different, right? But if we compute the standardized distance in the two distributions, then those distances, let me do this again. So this distance from the normal distribution with mean 500, standard deviation 100, and the other distance that I've computed, this other standardized distance from the standard normal distribution, these two are now on the same scale, right? So this distance, 47.7 and 0.51, they're now both on the same scale, right? Because I have standardized the distance by dividing it by the standard error. So, so the upshot of all this is that what we really want to do when we want to compute distance is we want to compute the distance on the same scale, in the same unit. And the unit that we are going to compute the distance in is the standard error, right? So we're going to compute the distance in standard error unit. So just when we say that the distance from here to, from Golm to Berlin is, let's say, 35 kilometers, that's the unit in which we are talking, right? We're not talking about meters or centimeters or something. But here we're talking about the distance in standard error units. And so we're always going to say that the distance is t standard errors. Okay, so that's why this t value turns up. And so what we're going to be doing is that we're going to be computing every time that we do collect a sample and compute the sample mean, set up a null hypothesis value. We're going to divide that distance, the distance between the sample mean and the hypothesized value, by the standard error, so that we can talk about the distance in standard error units. Okay, so this allows us to compare any distribution with any distribution, right? If you want to talk about distance in different distributions, like the two examples I showed you here, the comparisons, this standardized distance and this standardized distance are really on the same scale, right? So it would be, if I wanted to talk about how far away the sample mean is from the hypothesized mean in this distribution versus how far away the sample mean is from the hypothesized mean in this distribution, I can now actually talk about the distances in the two cases, which are very different distances, but those distances are on the same scale. One distance is very large and one distance is very small. This distance is very large because my hypothesis is that the mu is 0, where the mu is actually 500, right? In this case, my hypothesis is that mu is 0, and the mu is in fact 0, right? So the distance is small here, distance is large here, but they are comparable. The distances are now comparable because they're both on the same scale, right? We're comparing kilometers with kilometers in this case. So standard error is the unit here, okay? So the upshot of this is that whenever we compute a sample mean and a standard error, we are going to transform that to this t value here. So this is called the t value, or I will call it the observed t value because it's observed based on the data. And as you will notice, because the sample mean is actually, it has its own distribution, right? The normal distribution, that's the sampling distribution of the sample means. We are just transforming that sample mean into a new distribution that is into a new value called the t value. And that t value will therefore have its own distribution, right? So for example, what I'm trying to say here is that we could set up a situation that we repeatedly compute an observed t-value, right? And so I'm going to repeatedly run the following experiment 1,000 times. I'm going to run an experiment where I take a sample of size 100 from some distribution, right? Just choosing some arbitrary distribution here to sample from. And I could compute the mean of that distribution. And I could also compute the standard deviation of that distribution, right? And I could also compute the standard error of that distribution, which would be this quantity, right? And so if I were to divide the sample mean by the standard error, that would give me the observed t-value, because my hypothesized null hypothesis is that the null hypothesis is that mu is 0. right? So this is my null hypothesis. Here is the distance between the sample mean and the hypothesized mean, standardized by the standard error. And so these bracketings are very important because otherwise the division will be incorrect, right? So make sure that you get the brackets right. So this is my observed t-value now, right? So what I'm doing is I'm taking some sample data and I'm converting it, I'm transforming it into an observed t-value. I'm going from the data to the sample mean to the observed t-value. So I'm transforming the data to an observed t-value, right? And so what's interesting to observe here is that the t-value that I get from a particular experiment under repeated sampling, like in this for loop here, the t-value will also have a distribution. It's a random variable, right? And what will that distribution be? Let's look at it, okay? Right? Oh gosh, did I make a mistake? Sorry, that was a stupid mistake here. To put, I need to save, I need to save the observed t-values into this vector here. So that was a mistake. So what you see is that the observed t-value has a particular distribution, right? So suppose I was sampling from a standard normal distribution. Let's just take this one for an example and, and plot this distribution here. So this is the typical distribution that I'm talking about here. So this is the observed t-values under repeated sampling, right? And because I'm sampling from the standard normal distribution, that means my hypothesized value was that mu is 0, and the actual mu value is actually 0 because I'm sampling from the standard normal. Therefore, the average distance, the average value of the observed t value is 0. The largest value is near 0, and it has some standard deviations. This distribution of t values has a name, right? Surprisingly, it's called the t distribution, right? And so the t distribution is just like the normal distribution. It's a distribution, it's a probability density function. It's a continuous distribution. And it takes, just like the normal distribution takes two parameters as input, the mu and sigma, the t distribution takes the degrees of freedom as input. The degrees of freedom is defined as the sample size minus 1. Okay, I won't discuss the details of what this is, but the upshot is that once you know your sample size, n minus 1 will be the number that goes into this distribution that will describe the shape of this distribution. I will just make that more precise, okay? So, but the important thing to understand here is that we are now transforming the sample mean to a t distribution. The t distribution is defined in terms of um, the, the degrees of freedom, so n minus 1. So what we will write is that our observed t value from a single experiment is now coming from this distribution, right? Just like our data were coming from some distribution like the normal or something. So here, the observed t-value is coming from this distribution, right? I just want to make sure that, sorry, I just wanted to be sure that I'm actually recording. I forgot whether I was actually recording. I am. Very good. Okay. So, and so one other interesting thing to notice about the t distribution is that as n goes to infinity, as your sample size goes to infinity, the t distribution starts to look more and more like the standard normal distribution. And in fact, as n goes to infinity, the t distribution actually becomes the standard normal distribution. Okay. So when n is small, what happens is that the t distribution has slightly fatter tails than the standard normal distribution. I will just show you a picture of that. But the upshot is that the t distribution that we'll be using from now on will be defined the spread of that distribution. So how fat the tails of that distribution are defined by this parameter n minus 1, which is called the degrees of freedom. Okay? So what this means is that when we collect data with a sample size n, we specify our null hypothesis, and having specified the null hypothesis and knowing the sample size, we can actually draw the t distribution corresponding to the null hypothesis distribution, right? And for large n, we could even use the standard normal distribution to describe the t distribution, but people don't do that. They will always use the t distribution just for out of convention. But in future, in the coming lectures, I will always be using the t distribution regardless of what the sample size is. Need to close the window. Right. So So I've already explained this, so how the tree distribution is defined. It's defined in terms of the degrees of freedom. You can, of course, look up the equation for the t distribution. It might be in the textbook as well. But if not, you can find it on Wikipedia or something. But the one interesting thing that I just mentioned, which I want to now show you, is that the shape of the t distribution approaches the standard normal distribution as the sample size increases, right? So when you have only 3 data points, so n is 3, therefore the degrees of freedom are n minus 1, 2, right? So in that case, you'll notice that the t distribution, which is the broken lines here, has fatter tails than the standard normal distribution, which I've always drawn in a solid line here, okay? So as I increase the sample size, so this is sample size 6, you see that the tails get slightly closer to the standard normal. Was sample size 15, they're getting almost overlapping with the standard normal. And by the time I get to standard sample size 21, right? So degrees of freedom 20, I have almost overlapping distributions between the standard normal and the t distribution, right? So if I kept increasing sample size, I would literally overlap with the standard normal distribution. Okay? All right. So now we come finally to the one sample t-test hypothesis testing procedure. First of all, we start out by defining our null hypothesis. For example, that mu is equal to 0, right? And we collect some data of size n. So right now I'm assuming that the data are independent. So every single data point has to be independent, okay? So data of size n. We estimate the sample mean, estimate the standard deviation, estimate the standard error, compute the observed t-value, and then we reject the null hypothesis if the t-value is large enough, period. That's the entire hypothesis test, okay? So we're going to operate on the basis of the observed t-value. Right? So now the question is, how do I decide when the observed t-value is large enough or not? Right? How do I decide this? So intuitively, the way we want to quantify large enough for observed t-value is to say the following, right? So suppose that my t distribution is this one here, right? Right now I'm working with t distributions that are centered on 0, right? Later on I'll look at some other variations. So this is my hypothesized distribution, t distribution. So I'll write it like this: t n minus 1, whatever n is, right? And what I want to do now, what I'm going to do now, is I'm going to define a rejection point on the x-axis, right? So these are the t values. This is the t distribution, possible t value under repeated sampling, right? So what I'm going to say is that if I'm going to define two quantiles, Q1 and Q2, right? So these quantiles will be defined such that the area to the right of the second quantile is 2.5%, and the area to the left of the first quantile is 2.5%. Right, so in the t distribution, you also have the dpqr family of functions, right? So you can do, for example, RT, You can generate random data from, you know, you can generate 100 data points from a t-distribution with n minus 1 degrees of freedom. And you can do all the other calculations, the probability, the CDF and the inverse CDF and so on. Everything can be done with the t-distribution. So we define two quantiles that mark the cutoff points for our observed t-value. If our observed t-value lands anywhere if our observed t-value lands anywhere in this region, or in this region, right, to the left or right of these cutoff rejection points, then we are going to say that the t-value is far away enough, and we will reject the null hypothesis. If our t-value lands within this region, this is the non-rejection region, and so in that situation, if our observed t-value lands within this non-rejection region, then we fail to reject the null hypothesis. So I'll call this the rejection region, right? I'm talking about the x-axis here, right? The rejection region. So my observed t-value can land anywhere on the x-axis, right? If it lands in the tails of the distribution, that's a very unlikely value, assuming that the null is true. Therefore, we reject the null. And if it lands within the non-rejection region, that is the blue region here, then it's possible that the null hypothesis is true, so we fail to reject the null, okay? All right. So that's basically what I'm quantifying, showing you here graphically, right? So we are looking at a t-distribution with n minus 1 degrees of freedom, and I've colored the regions where the probability under the area under the curve sums up to 5% if you sum up the left and right tails of the distribution. This distribution is symmetric, by the way. When the t-distribution is centered on 0, it is symmetric, okay? So in this symmetric distribution, the area under the curve to the left and right of those rejection points sums up to 5%, and each side has 2.5% area under the curve, right? And so why is it 5%? It's just a convention. I could have chosen 1%, so then I would have 0.5% on the left-hand side and 0.5% on the right-hand side. I could have chosen 20%, in that case, there would be 10% on each side, right? So this is an arbitrary decision that we are making to have a cutoff, a rejection point such that the area of the curve in the extremities, in the tails, is summing up to 5%. Okay? And so the whole procedure amounts to checking whether your observed t-value lands in the rejection regions, in either of the rejection regions, or whether it lands in the non-rejection region, right? Right. So this is what I've just explained here, and you can now decide what that rejection point is by using the QT function, right? So you can find out what's the quantile such that 2.5% of the area under the curve lies to the left or right of it. So notice that I'm just computing the absolute quantile value because I don't really care whether, I compute the area to the left of the lower quantile, right? So let's go here. Right, so in this example, this quantile Q1 and Q2, this quantile Q1 and Q2 will be exactly the same number, just with opposite signs. So this will be approximately +2, this will be a -2, right, approximately, right? So that's what I'm computing here. So I'm just computing 2.5% of the area under the curve to the left of um, so I'm trying to find out what is the quantile such that 2.5% of the area to the curve, area under the curve is to the left of it, right? In a situation where I have 16 data points. N minus 1 is 15, therefore I have 16 data points, right? So with the answer and what I'm computing is the absolute value, because if I were to just compute this quantile, let me just do this. If I were to compute this quantile, I would get a negative number, right? Right, so I would get minus 2.13. But what I want to know is what the absolute t-value is, because I don't really care what the sign of the thing of the t-value is, because I know that whatever quantile I have on the left-hand side, I'll have the same quantile on the right-hand side, but with a different sign, with the opposite sign, right? If we go back to this figure, right? So here I know that these two numbers will be identical, right? Q1 and Q2. And so as soon as I just want to know the absolute value, because I know that one will be negative and the other will be positive, because the center point is 0, right? That's why I'm looking for the absolute value here, okay? So, so now I know what the cutoff point is, plus minus 2.13, right? If I were to increase the sample size to 51, notice what happens for the same question. Now my critical t-value becomes 2.0. So this makes a lot of sense if you go back to the earlier plot that I showed you, right? So the difference between this sample size and this sample size is that the tails are fatter when the sample size is low. That means you have to go out further to cover 2.5% of the area under the curve on the edges, on the tails of the distribution. If the distribution gets tighter, that means if the tails become smaller, right, or lower, then your cutoff point will also go in a little bit. That's why for larger sample sizes, you end up with um, this, this cutoff point of 2 instead of 2.13 when you increase the sample size, okay? So these t-values, these are t-values that we are computing, because as you can see in my iPad, right? So these are critical t-values that I'm computing. These are called critical t-values. And they're called critical t-values because they are defining the cutoff point for making the decision of accepting, or rather of rejecting the null hypothesis or failing to reject the null hypothesis, okay? Of whether we land, depending on whether we land in the red region, in this region, in the rejection region, in this rejection region, here, or here on the left-hand side, or whether we land in the non-rejection region, which is this region here, right? So we make our decision whether to reject or not reject depending on where the observed t-value lands. And in order to make that decision, we define these critical t-values, which are dependent, of course, what the critical t-values is depends on the sample size, right? Because the sample size determines the shape of the t-distribution. For lower sample sizes, you have fatter tails, so you have to go out further to get to the critical t-value. And for larger sample sizes, the critical t-value will become smaller, and that's what I just showed you in my slides. All right. So, so let's go back to our running example. I had a sample earlier that I had computed the sample mean from and this estimated the standard error from. I have a null hypothesis mu, which is that mu is 0, right? And from this information, I can now compute the observed t-value, right? This is the observed t-value because it's x bar minus hypothesized value of mu divided by the standard error. I get a value like 4.17. Now, 4.17 is clearly going to be in the tails of the distribution, right? And how do I know that? Well, if my sample size was 11, right? How would I find out what the critical t-value is? The critical t-value for sample size of 11 would be, I'm going to use the quantile function, right? What is the quantile such that for degrees of freedom 11 minus 1, right? What's the absolute quantile value that constitutes my rejection points, my rejection points in the distribution? It's 2.22. So if my observed t-value is actually larger or smaller than 2.22, it could have been smaller, by the way, right? It doesn't matter what the sign is. If it is more extreme than the critical t-value, that implies that it's lying in the tails of the distribution, right? So in this example, if my cutoff value is, critical value is 2, and I get an observed t-value of 4, that means I'm landing somewhere here. I'm landing somewhere here in my, based on my data. So I'm landing in the tail of the distribution. And so in effect, I'm landing in the rejection region. Therefore, I would reject the null hypothesis by just looking at the observed t-value, right? The observed t-value is 4.1 something, right? That leads to a reject decision, reject null. Because the observed p-value is very unlikely, very improbable, right? Given the null hypothesis distribution, which is described by this distribution centered on 0, right? That's the idea here. Okay. So so this slide is just talking about how to compute the exact critical t-value, right? The exact critical t-value, as I said just now, depends on the sample size. But for large sample sizes, you can approximately take plus minus 2 as your critical t-value. Because as the sample size goes up, the critical t-value will approach, you know, will approach 2. So I'll show you this in a moment. Let me show you. So I will compute the quantiles, right, for 0.025 for, let's say, degrees of freedom 5, okay? That means 6 data points. That gives me minus 2.5. So I'll just compute the absolute value like always, right? I won't look at the sign. So that's 2.5. Now, if I increase this number to 50, or let's say, let's increase it to 10, the number starts getting smaller and smaller, right? So okay, let me see if I can do this, 5 to 50. Can I do this? Yeah, this works, right? So I'm computing for different degrees of freedom. So increasing sample sizes, I'm just computing the absolute t values. And you'll see that, let me just go up to 5,000, 50,000 or something. You'll see that the further I go, so let me just save these observed t values, right? So if I show you what the observed t values look like as I increase sample size, so let's do this. Let's plot this, okay? So I'm going to plot the observed t-values for each of the sample, sorry, not sample sizes, for each of the degrees of freedom. I'm going to plot the observed t-values, and you'll notice that the observed t-values, for smaller degrees of freedom, like 6 or like 5 or something, they are very large, like 2.5 something. But as you increase sample size, the observed t-value, these observed t-values, they approach 1.96. 1.96 is the, the quantiles for the standard normal distribution, if you remember, right? So 95% of the area under the curve, right, around the mean of 0 in a standard normal. Let me draw this. So just to remind you, in a standard normal distribution, right, centered on 0, 95% of the area under the curve, this area under the curve, right, lies between plus minus 1.96, right? And so as you increase sample size to 50,000 in my example, right, in my R code, as we increase the degrees of freedom to 50,000, that means we go to 50,001 sample size, right? We basically end up with I shouldn't have called this observed t-value. That's a mistake. What I want to say is that the critical t-value. Sorry about that. When you're talking fast, you tend to not think about what you're doing. So here, right? So this is the critical t-value that is now approaching 1.96. So this is basically exactly the same point that I made earlier, which was that the you have the standard normal distribution, right? And for low sample sizes, right, the t distribution will have fatter tails. Therefore, the critical t value will be larger. But as you increase the sample size, the critical t value will become the same as the standard normal distribution's t value, which is 1.96, right? So that's what I was just demonstrating here. All right. So for that reason, because of the fact that for large sample sizes, the critical t-value is going to be about 1.96. So let's call it plus minus 2 as usual. I like to just use plus minus 2. So what we will do is for large n, let me write this down. For large n, I'm going to just assume that my critical t-value is 2. I'm going to say plus minus 2 because this is the absolute t-value, or rather more accurately, absolute critical t-value. Right? So, right? So for large n, I will just assume a critical t-value of 2, absolute critical t-value of 2. That means if my observed t-value is larger, the observed absolute t-value is larger than 2, that means I can reject my null, right? For smaller n, you would want to compute, so for smaller n's, right, you want to compute the exact critical t-value that will allow you to decide whether to reject the null or not based on the observed t-value. And how would you do that? You would compute the absolute quantile such that the area under the curve to the left of it for whatever degrees of freedom n minus 1, the area under the quantile is 2.5%, right? So this would be the exact critical t-value, but for large n, you can just get away with assuming that plus minus 2 is your critical t-value, right? Okay. Now, the last thing I want to tell you is that suppose you do your experiment. So we did that experiment earlier, with, what was it? My example data set, right? My simulated data. I had computed, just one second. I'm sorry, I lost it. Here, right? So here I computed the t-value of 4.17. I think my sample size was 11, right? So let me just write down all this and then I will show you what I'm doing. 4.17 and sample size is 11. So what we are going to do is, on the one hand, we already know that our decision is going to be reject. We want to reject the null hypothesis, right? We already know that because the observed t-value is larger than 2, okay? But what we can do is we can actually calculate the probability of observing the observed t-value. So I'll call this the observed t-value from the data. That's what we observed. The probability of observing such a t-value or something more extreme Given, so that's the vertical bar, that's a conditional statement, given that the null hypothesis is true. Okay, so we're going to compute this probability. Now, think about it, okay? We've got the null hypothesis t distribution centered on 0. Our observed t value is somewhere out here in the tail of the distribution, somewhere here, 4.17, right? And so what we want to compute is the probability of observing this value, 4.17, or something more extreme. So that's the area under the curve here. And we won't even stop there. What we also want to compute is the probability of observing minus 4.17 or something more extreme. So really what we want to, the question we are asking when we are computing this probability is, what's the probability of observing the t value that we observed or something more extreme in either direction, right? Notice that we only observed a t value of 4.17, but we asked the question about both directions. What is the probability of observing something as extreme as 4.17 in either direction? Okay. What's the probability of observing 4.17 exactly? That's 0. It's a continuous distribution, right? So the only question we can ask is, what's the probability of observing something like 4.17 or something more extreme in either direction? And that is the area under the curve to the left and right of 4.17, plus minus 4.17, right? So this probability is called the p-value, and of course, you know how to compute it, right? If you know the degrees of freedom, you can use the PT function to figure out the probability of observing such an extreme value. So let me do that for you, right? So if my observed t value is 4.17, right? I'm going to use the PT function to figure out what the probability is of observing this value of something more extreme, right? Given degrees of freedom 10, because 11 minus 1, right? And I'll say lower tail equal to false because I'm looking at the probability to the right of 4.17, okay? I'm computing this probability here. And because this is a symmetric distribution, if I know the right-hand side probability, I know the left-hand side probability, this one as well, right? So I'm just going to multiply the probability I get by 2. This probability, this number here that I get, I'm going to multiply it by 2. And that number is that 0.0019 is my p-value now. That's the p-value. 0. What was it? I already forgot. 0.0019. 0019. So this probability is the probability of observing the t-value that we observed or something more extreme in either direction, assuming that the null is true. Okay. So so here I'm just showing you how to use the PT function, but you guys know how to use that already for the p-norm case. So this is just a generalization of that to a new distribution. And so what I want to show you now is that we could have taken our observed data, the sample data that I had, that I was using as my running example, and run it through the t.test function. Okay, if we had run it through the t.test function, one of the things that the t.test function would print out for us is the t statistic. Okay, that's 4.17. That's the number I've been working with so far. And so the t.test function will print out for you the sample mean, the 95% confidence interval, the observed t-value, the degrees of freedom, and the p-value. Right? These are 5 pieces of information that you will get when you run the t-test. So let me see if I can actually do this with in the code that I have. right? So let me see if I can find my sample data. Where's my data? Oh, where is it gone? Let me just make up a new data set, okay? Let me just do this. Um, yeah, I think it's okay if I just make up some new data set, okay? So let's do this, right? So I'm going to create a sample. I'm gonna collect, let's say, 11 data points, right? 11 data points from a distribution with mean 12 and standard deviation 4. I'm just making these numbers up, okay? It could be any arbitrary number, right? So now these are 11 data points. There are 11 independent data points, actually, right? And so what I'm going to do is, if I run the t.test function, if I run the t.test function, it will print out a statistical test for me. It shows me what the observed t-value is. It tells me the degrees of freedom. It tells me the p-value, right? And it tells me the 95% confidence interval. And it tells me the mean of the distribution that the sample mean from the data that I have. Okay, and so this is the one sample t-test, right? I could have computed all these quantities, this probability, this t-value, these confidence intervals, this sample mean, all of this I could have done by hand. Let me do that, okay? Last thing for today, I'm going to compute the mean of the sample, right? I'm going to compute the mean of the sample. I'm going to compute the standard error, which is sample standard deviation divided by square root of 11, right? That's my standard error, right? So that's my mean, that's my standard error. So I'll write down standard error here, right? Because I need it. I call this M for mean, right? So now I have the mean and standard error. And now I want to figure out my critical t-value. What's my critical t-value for sample size 11? It's going to have to be this absolute value, which is um, degrees of freedom 10, because 11 is my sample size. So now I get the critical t-value, which is 2.25. Therefore, now if I type mean minus critical t-value times standard error, that gives me the lower bound of the confidence interval. If I want the upper bound of the confidence interval, upper bound of the confidence interval, I do mean plus critical t-value times standard error. Remember, the critical t-value is telling me the cutoff point such that the total area under the curve to the left and right is 5%. So this should be my confidence interval. Unless I've made a mistake, this should be exactly what the t.test function will give me, right? So I'll print this out, right? Okay, what else will I get? I'll get the observed t-value. Let me compute the observed t-value, which is the sample mean divided by the standard error. Because remember, sample mean minus 0 is just a sample mean. So I could have written this, but I was just skipping that step. So that's my observed t-value. So I should get the same observed t-value as in the t-test. And the p-value is going to be pt observed t-value, degrees of freedom 10, right? Lower dot tail equal to false, right? And multiplied by 2, because I'm looking at the two extreme ends of the distribution, the total probability of getting a value as extreme as I observed, or something more extreme in either direction, right? So all these numbers should match up perfectly with my t-test output. So let's compare, okay? Unless I made a mistake, I should get exactly the same numbers. So sample mean 13.255 according to the t-test. What is my sample mean? 13.255. Then next thing, the 95% confidence interval. Let's compute that. right? The lower and upper bounds are 10.41 and 16 point something. There we go, 10.4, 4, there's some rounding errors here, okay, but it's roughly the same. 10.44 and 16.06. So when the computer is computing all these things internally, because of rounding errors, you can end up with decimal points that are slightly different. But these are all on the same ballpark, okay? So I have the confidence intervals and the mean down. So let's compute the observed t-value. What was my observed t-value? 10.50. What does the t-test say? 10.50, right? And what's the p-value? The p-value according to this guy is a very small value close to 0. That is 1 times 10 to the power of minus 6. That's what this scientific notation means. So let's compute the p-value. All right, we have exactly the same numbers. 1 times 10 to the power of minus 6. So basically, what I've shown you is that the output of the t.test function will take as input n independent data points. This is the one sample t-test, okay? Take n independent data points and it will compute all these 5 statistics for you and report them for you in a summary, okay? So we're going to get some practice in doing this one sample t-test in the next homework assignment. So I hope that it's clear now how the one sample t-test arises. The next step will be to get some practice in working with the one sample t-test. We will work with the Stroop data and some other data sets to get a feeling for how we would actually compute all these statistics one by one, given some independent data of the type that we have already collected in the Stroop experiment. So that's it for now, and I'll see you in class.